just a quick reminder of where we left off. We had talked about what half-life was, how nasty it is, it's terrible, it creates lots of problems with radioactive elements, which is one of the big issues with nuclear power, was what to do with the leftovers. So for example, suppose a nuclear power plant wanted to use this cobalt-60, they have 100% to start with, and then it's decaying. So I gave you this box right here that shows how to do these formulas. So half-life is always A, which is your starting amount, times the half-life to the T over whatever the half-life is. And then decimal approximation finds 1/2 to the 1 over half-life and substitutes it. Okay? So I gave you this example here. We had 100% to start with. There's the exact equation right there. And then we found the decimal approximation by using our calculator to do whatever 1/2 to the 1 over 5.3 is. Okay. Then we found h of 20, which is right there, 7.312. And now the question is, what does it mean? Good question. All right, so it means that now what was our beginning year? Oh, they don't even tell us. Okay, so in 20 years, there will be, now this was a percentage problem, so it said percent, so that's why we started off at 100 for 100%. So we would say 7.312%, or excuse me, how about this? 7.312% of the cobalt 60 will remain in the tank. Okay? Doesn't sound promising, but that's how it is. And again, if they had given you grams, like in science class, a lot of times they won't do percentages, they'll do grams. So they'll say, if you have 100 grams, and then you'd say 7.312 grams or whatever. But in this class, we do a lot of percentages. All right, now here's the tricky part, and this is the part we were talking about a couple pages ago, which is the whole decay thing. So if it's decaying, that means something very specific in terms of your rates, all right? So matter of fact, I'm going to give these little boxes. That's nice. Okay, so remember, if the decay rate is 5%, that means that our base was 0.95. Remember that? Why? Well, because you take 1 minus your rate will get you your base. So let me put that in here, right? For decay, let's remind ourselves, the base is equal to 1 minus the rate of decay. Okay? So you found that your base was 0.8774. That must be equal to 1 minus the rate of decay. Okay, so you need to figure out, okay, 1 minus this rate of decay is equal to this number. So how could you find what the rate of decay is? Well, you can fiddle around with it a little bit and you'll see that it has to be, here, I'll solve for it. Okay. Here, let me put it in the equation. That'll help. Let's see. Okay, so oops. There we go. So you'd say, okay, my base is equal to 1 minus my rate of decay. So can I just call this rate? That'll be easier. R, even R for rate. Okay, so if I add R to both sides, right, I can do that. Then over on the right, they're going to disappear because R minus R cancels, right? Negative R plus R is gone. So that gives you R plus 0.8774 is equal to 1. Now you want to solve for R, so you want to subtract the 0.8774. I'm just occurring to me that I could have just subtracted the 1 in the first place, but that's all right. I did it this way. It's fine. Minus 0.8774. So this will be gone over here. Make it disappear. So you're going to be left with R is equal to 1 minus that. Okay, so R is equal to 1 minus 0.8774. In other words, it's the difference between the rate and 1 that really matters. So let me grab a calculator. Go 1 minus 0.8774, enter. Gives me 0.1226. All right, so let's keep that in mind. Just all of this is really an aside. It's side note. It's not really the main part of what we're trying to answer. None of this is the actual answer or anything. It's just me trying to make some notes for us. Okay? Okay, so if that's all the case, if that's all true, what's our base? Our base was, let's see, 0.8774. So what does that mean? That means that we just found it. Our rate of decay is equal to, and I found it right down here, 0.1226, right there, which is really 12.26%, right? If you were going to write it in a percentage. So our rate of decay is 12.26%, and that's what you use to explain it. So you say every year there is, how about this? Every year we lose 12.26% of the cobalt 60 in the tank, right? You're losing 12.26%. That's the answer. Okay, so it's a little convoluted, but you really don't have to do this much work. I was just kind of showing you the by hand work, but notice, here, let me put it this way. Oopsie. Notice what these two have to add up to. 0. This number 0.8774 and this number 0.1226 have to make 1, because 1 is your flat line, right? So if 1 is your flat line amount and your base B is at 0.87, that means you lost 0.1226. You see? So you take it away from 1, and that's your rate of decay. All right? So remember, we did the opposite back when we were doing this stuff. So here we said, oh, it's growth. Growth rate is base B is equal to 1 plus the growth rate, which made 0.119. Plus because it was growing. But for decay, it's the opposite. You say, okay, my rate base is equal to, it's right here, base is equal to 1 minus my rate of decay. Right there. 1 minus r, if you will, like that. And if that's the case, then you have to do the subtraction part. So you say, okay, I got 0.8774, take it away from 1, and there I've got my rate of decay. That's what I'm losing every year. It's a little funky, so you really got to pay attention. I think the adding ones, the growth ones, are a little bit easier to see, but the decay ones are a little bit harder. Speaking of growth and decay, let's remind ourselves. Oh, and these were wrong. As I recall, this one's actually 2.5, and the other one was 4.0. So let me put these in. Those were typos, so fix those. All right, so we had this back in section 4.3. So we had these 4 functions, and we labeled each one of them. Let me go put the labels back in. So actually, let me remind you. So which one's which? So remember that and this was it, the farther that we are from 1, the steeper the graph's curve. Steeper, not stepper. Steeper. The closer B is to 1, the shallower, less steep, if you will, the graph's curve. All right, so remember we learned all of that, and let me put these in. So which one is, oh, and let me also make a note. Okay, remember that if B is greater than 1, so if you have B is equal to 1.25, or B is equal to 1.40, there we go. So when it's 1.25, 1.40, they're both exponential growth, right? Because it's bigger than 1. Remember, if it's bigger than 1, that's growing. And the rates of growth are 0.25 and 0.40 respectively. 0.40 is a bigger number. That's why it's a steeper graph. So if you look at the two of them, it's kind of that mustardy yellow one. That's the 1.40 one. Hold on one second. Let me label it. There we go. So there's the steeper one. It grows faster because it has a faster rate of growth. It's got a bigger rate of growth there. Okay? And that backs up what we were saying, that a steeper graph, and that's your rate of growth. And by the way, that's what it says at the top of the next box. If B is greater than 1, then the quantity grows at a rate of B minus 1. Basically, you take it away from 1, or take 1 away from it. Right? So the rate of growth is 0.25, 0.40 respectively. All right, now let's deal with the decay ones. We had 0.65 and 0.80. Okay. Oops, sorry about that. Now who's steeper? Well, it's got to be the 0.65. Now here's why. They have exponential decay, right, at a rate of 35% and 20% because you take it away from 1. That's what we were just talking about on the previous page. So with the half-life, you subtract from 1, right? So it's 35% and 20% respectively, which means that the 0.65 is steeper, right? Because it's farther away from 1. So it should go, and we already had these pictures, so this shouldn't be coming as any great shock to anybody. This one's 0.65, and the next one is 0.80. I should probably do this while I pause, but yeah, it doesn't hurt you to see how it's done. Okay, so there you go. Right? Okay. By the way, while I'm on the subject real quickly, just on a side note, if you wanted to go steepest of all 4 graphs to least steep, shallowest, let me put it this way, shallowest. Actually, let's do it the reverse. Let's go shallowest to steepest. Let's go from the to steepest. How would that look? Well, the shallowest one would be the one that has the smallest rate of growth or decay, which would be this one, the 0.20, which went along with the 0.80. So the shallowest one is actually g of x, which is 0.80 to the x, right? Because it has a rate of only 20%, right? Difference from 1. Then the next one would be the next number, which would be 0.25. So to be 1.25 would be next. That'd be the next shallowest because it's the next smallest number for growth. And then 1.35 would be next. So 0.65 would be the next steep. And then, let's see, the 1.40 has the biggest number with it. So it'd be the steepest, right? So there you go, shallowest to steepest. I know it didn't ask it, but hey, it doesn't hurt you to spot it. Helps keep you honest. And then again, it's because of these rates. The ones with the smallest rates of growth or decay would be the shallowest. The ones with the steepest rate of growth or decay would be the steepest, right? Largest. And that subtraction thing that I was just doing, that's right here in that box right there. Right? I subtract from 1 or take 1 away from it.